Okay, so this is part two of the notebook that accompanies chapter two of the textbook Mining Complex Network. And in this part, we're going to actually compare different random graph models that we already considered with a real graph. And in this case, we're going to be looking at a graph that we saw already in chapter one, which is this GitHub machine learning developer graph. And we're going to be comparing different characteristics of our base graph or our real graph with four random graph model, namely the binomial or Erdős-Rényi, the Cheng-Lu, where you keep so with the Erdős-Rényi, basically you only pass the average degree or the number of edges. The second one is the Cheng-Lu, where you preserve the degree distribution, but in expectation. The configuration model, where you preserve the exact degree distribution, and then a variation of the configuration model where you obtain connected simple graph. Okay, so let's run this here, where we're basically, the only thing I'm doing here is the same we've done in chapter one, is to read, the data, read the attributes, build dictionaries, build the graph, the GitHub graph, and then build the subgraph where the class is equal to ML, so the ML developer subgraph, which has, this number of nodes and this number of edges. Let's run this, we're also going to be using this base stats function. So given a graph, an iGraph object G, we're going to be returning a bunch of basic statistics. So V count is the number of nodes, number of edges, the min, mean, median, and max for all the degrees. We're going to be looking at the diameter of the graph. We're going to be looking at the number of connected components, the size of the giant component, the number of nodes that have 0 degree, which can happen in some of the model. We'll see that. The clustering coefficient, the global clustering coefficient, which is also called transitivity, and the average local clustering coefficient or average local transitivity. Okay, so I'm going to run this for the different graphs and store it in one big, list of lists, which I'm then going to transform into a nice data frame for display. So it's already finished, but let's go through it. So first here, I compute the basic statistics for my real graph, subgraph underscore ML, and store that into a list where I prepend this title here, base graph. Okay. Next, I'm going to compute the base statistics for the Erdős-Rényi. In the Erdős-Rényi, I'm going to use the same number of nodes as my reference graph, of course, and the same number of edges, but those are really my only parameters. Next, I do it for the Cheng-Lu. And for the Cheng-Lu now, I'm going to use the degree distribution. So I have a degree distribution that I can pass, and I know how many edges I have. And I pass that to this fast Cheng-Lu function that we introduced in the first part of this recording. That is going to return a bunch of edges in the form of a list of tuples, which I can use in this to build this graph here. So the way I do it, I kind of build an empty graph with the proper number of nodes, and then I just add the edges. That's one way of doing it. The next one is the configuration model. So in the configuration model, we pass the degree distribution, and then by default, method simple. But again, the configuration model, if we pass method equals VL, then we get this variation where we get, for example, connected and simple graph that is guaranteed. And so the resulting list of lists I can store in a data frame with nice, column names and all that. And this is what we get. So let's look at this. So this is our base graph. Number of nodes, number of edges is the same for all of the models. This is my minimum degree, which is 1 for the real graph, and the maximum degree, which is 482, and then the mean and the median. And you can see that some of the model will preserve that. Okay, for example, the configuration model, but something like the Cheng-Lu, you could have degree 0. Erdős-Rényi, you could certainly have degree 0, and the median also is going to be potentially different in those models. The diameter is going to be a bit smaller for the Cheng-Lu, And it's also slightly smaller for the configuration model in this case. But one of the key point here is the components, the number of connected components. You can see the base graph has a single connected component, but every other random model here, especially the Cheng-Lu model, can have a multiple number of connected components, unless for the configuration model we use this variation where you will have a connected graph at the end. And this is the size of the largest component and the number of isolated node, which is kind of something that happens frequently if you use Cheng-Lu model, where the degree distribution is only recovered in expectation. Other thing to notice for the clustering coefficients, the values are particularly small for the Erdős-Rényi, actually very close to zero, slightly larger for the other models where we do preserve degree distribution, either exact or in expectation, but still a little smaller than what is observed in the real graph. Okay, so next thing we're going to look at is the distribution of the shortest path length for the different models. So let's run this and then we can go through it. So in this case, doing an all pairs, like compute the shortest path from every node to every other node, can take quite a long time. So I'm going to sample basically. So what we're going to be doing here, and for the disconnected graph, we're going to be looking at the giant component because we're looking at shortest path distribution. So these are the three random graphs that are potentially disconnected, as we saw here. So the ones that have more than one connected component, for those we're going to use the giant component. Okay, and what we're doing here is that we're taking a sample size of 200 in this case, and looking at for the different graph this function. Yeah, the function is dot distance. It did change between versions of iGraph. So the function we're going to be using is this function dot distance from vertex v for 200 different vertices v, and that's going to give the distribution of all of the shortest path length from vertex v to all the other vertices, and we're only going to keep the values that are strictly positive because we don't path length from a vertex v to itself is equal to 0 is also returned, but we're going to ignore those. Okay, so we're doing that for the real graph, our subgraph ML, for the Erdős-Rényi, for the Cheng-Lu, for the configuration model, and the variation of the configuration model. Okay, so this is complete, and then we're going to plot the result. This again, we saw that before. This using axis here, we're going to arrange the plot in this nice format here, 3 and 2. So one row with 3 and one row with 2, and we're going to make sure we have the same, range for the y-axis and the x-axis and what have you. So all of those are just to make the plots pretty. So we're plotting histogram for all the graphs with the different titles, and this is getting uniform x and y ranges. And because we don't have 3, 3 but 3, 2, the second row has to be adjusted a little bit, and adding the labels. And to each of the histogram, we're going to add the mean value for the shortest path distribution. And one thing here to notice is that for the for the base graph, the mean value is 4.51. For the binomial, you get slightly larger result, but and for the Cheng-Lu, the value is slightly smaller. One of the reasons is that the connected component, giant component, is smaller, is much smaller here. So things are a little more compact in this case. And then for the configuration model, the values are closer to our base graph. For the binomial, the value being larger is partly due to the fact that in an Erdős-Rényi or in a binomial random graph, you don't have like those huge degree nodes, the hubs that you have in the other models. Right? So, for example, if you get back to this table here, if you look at the Erdős-Rényi, your maximum degree is just 17, while the other ones are all in the like 400s. And of course, having some nodes with very high degree will make a lot of the shortest path much shorter, much smaller, just because those hubs connect a lot of the nodes together directly. Okay, so the rest is just extra material, so we're going to go a bit quickly here, but this is basically doing this power law test, but for that we did earlier for a graph that we generated ourselves, where we knew there was a power law distribution for the degree, but kind of redoing exactly the same kind of test, but using some of the real graph that we have. So if we do it for the ML, for example, we get pretty good agreement. So we saw those plots and those results before, but you can see that there is, a very strongly power law distribution for the degree in this GitHub ML subgraph. In the GitHub web subgraph that we also saw in chapter 1, situation is the same. It's pretty good agreement with power law distribution. And then the other graph we saw in chapter 1 was this grid graph, power grid. In this case, power law degree distribution is probably not a good model, and indeed, you can see there's more significant discrepancy between the power law fitted model and the actual empirical values. And the last part of the notebook, I don't think it's covered as per se in the chapter, but it's potentially required for one of the question. So it's a concept that was introduced in chapter 1, but the concept of independent set. So an independent set is a set of vertices in a graph where no two vertices, no two nodes are adjacent. So this is just a simple function to generate a graph, a random graph, an Erdős-Rényi graph, where we force to have an independent set of size S. So basically generate n minus s nodes and then add the s nodes, making sure that they're not connected to each other. Right? That's all this is doing. And this is showing that if we generate such a graph, G, and here we have 50 nodes, we're forcing an independent set of size 10, and the average degree is quite high, in this case 20. There's this function largest independent vertex set in iGraph that will actually find those, and we can print, this is, for example, it has size 10, this is what we ask for. We could have something of larger size, but with average degree that high, it's more improbable. But this is our independent set of size 10, and we can look at the graph, which is quite dense, and those are basically the 10 vertices that form an independent set that don't have any edge directly between any pair of those red edges. So that completes the notebook for chapter 2.